Hello, it's José Odreman who's speaking, and welcome to Module 5, Variogram Analysis. In just 20 minutes, you'll master the variogram, a key tool in geostatistics. You'll learn how to build and adjust variograms, detect anisotropies, and apply these skills to 3D models to enhance your decision-making in exploration and production. This is your chance to take your career to the next level. Are you ready? Let's get started. The variogram is a key tool in geostatistics that quantitatively describes how a property varies as a function of the distance between data points. It's based on the principle that 2 points close together are more likely to have similar values than 2 points farther apart. There are two main aspects of the variogram. How similar are two values that are right next to each other? At what distance do points stop being related to each other? The variogram is crucial for understanding the spatial continuity of subsurface properties, allowing you to make more accurate predictions in geological modeling. This image represents a variogram, which shows how a subsurface property changes as the distance between 2 points increases. Nugget. It represents the initial variability at very short distances, which can be due to measurement errors or very small variations. Sill. This is the maximum variability, indicating that after a certain distance, the properties are no longer spatially correlated. Range. The distance where the sill is reached, marking the point where data points stop influencing each other. Experimental variogram. These are the measured points that show how variability changes with distance. Variogram model. The red curve that smooths these points to make more accurate spatial predictions. In summary, this graph helps us understand how subsurface properties change with distance and is crucial for building accurate geological models. This diagram illustrates the search cone parameters used in geostatistical analysis, particularly for variogram calculations. The search cone defines a spatial region from which data points are selected along different directions to evaluate their correlation in a geological model. Here are the key parameters. Azimuth. This is the horizontal direction of the search cone, measured in degrees from the north. It defines the main orientation of the cone on the horizontal plane, from north to east at different angles. Dip. This refers to the inclination angle of the search cone in the vertical plane. It controls how the cone tilts downward or upward relative to the depth axis. Lag distance. The distance between sampling points along the selected direction. In the diagram, you can see how different lags, lag 1, lag 2, etc., are distributed along the main search direction. Lag tolerance. This defines a margin of allowable variation in the distance between sampling points. It means that points don't have to be exactly at the specified distance, but can fall within a range of tolerance. Tolerance angle. This defines the opening angle of the search cone. The larger this angle, the more data points can be included within the search region. Bandwidth. The width of the cone, which specifies how wide the search range is in the direction perpendicular to the main axis. It controls how many points are considered along the search direction. Thickness refers to the vertical extent of the cone. It determines how many data points are included within the cone based on its vertical thickness. In summary, the search cone uses these parameters to define which data points will be selected and how they are spatially correlated in geostatistical analysis, crucial for determining spatial continuity in geological models. Let's walk through how to compute a variogram step by step, using the image as a guide. First, we start by defining something called lag distance. Imagine you're working with a dataset, and you decide to look at how the data behaves between points that are 10 meters apart. That's our lag distance. Basically, the spacing between any 2 points in your data. Now, you will compare all pairs of points in your data that are exactly 10 meters apart. For each pair, you calculate the difference between their values, square that difference, and then start collecting these results. You plot them using something called an H-scatterplot in Petrel, which helps visualize how values change with distance. Next, you sum up all these squared differences and divide by the number of pairs n to get a variogram value for that specific lag distance. This gives us one data point on our variogram graph, the dot shown in the figure. To compute the semi-variogram, which is more common, we take that result and divide it by 2n. You repeat this process for other distances, say 20m, 30m, or 40m, and each distance gives you another point on the variogram. Now, we move on to creating an experimental variogram, which is essentially a collection of all these points, each representing the variation at different distances or lags. These points form a visual representation of how the data is related over distance. The final step is curve fitting, shown as the red line in the figure. By fitting a curve to the experimental variogram points, we generate what's called a variogram model. This model helps explain the pattern of variation over distance in a much clearer way. In summary, the dots in the graph represent the experimental or sample variogram, which is calculated from the data. Each dot shows how much the values change, on average, over a specific distance. The red line then explains this behavior with a smooth curve of variogram model, which we use for analysis and predictions. Let's talk about the Simbox mode in Petrel. But don't worry, we'll keep it simple and interesting. What's the deal with Simbox mode? Imagine you're looking at a bumpy landscape with hills, valleys, and faults, and you're trying to understand how something like porosity or permeability changes underground. It's a mess, right? Simbox mode comes to the rescue. It takes all that complexity and flattens it out, turning everything into neat little boxes. It's like looking at the land through a flattened chessboard, where all the cells are the same size and everything is organized. Why would you want to use this? Horizontal analysis. When you're trying to figure out how properties change across a layer, like east to west, Simbox mode is perfect. It makes sure you're comparing apples to apples, only looking at data from similar layers. Vertical analysis. Here's the thing: Simbox mode isn't as helpful when looking at vertical changes up and down along wells. If you want the real data on how things change vertically, it's better to turn Simbox off and work with the raw, unflattened data. When should you turn it on? If you're building a geological model, keep Simbox mode on. Petrel uses it to make calculations more accurate when working horizontally across layers. But if you're adjusting vertical resolution, turn it off. You want the true variation from well logs to get the right grid size for your model. One more thing. The variograms, those graphs that show how things vary over distance, shouldn't look too different when you switch between raw and upscale data. If they do, something's off. Bottom line, Simbox mode is your go-to for clean, horizontal analysis, but when it comes to vertical variability, turn it off to get the real picture. Used right, it'll help you build super accurate geological models. All right, let's take a look at this image showing a reservoir model in Simbox mode. The first thing you'll notice is how uniform and flat the zones appear. That's thanks to Simbox, which flattens the geological structure, making it easier to visualize the porosity and permeability properties. Now, let's focus on the colors. The colors here are key. Yellow and red tones represent areas with high porosity, meaning zones where fluids can flow more easily. On the other hand, the green and blue tones indicate lower porosity, where fluid movement is more restricted. What is this image telling us? First, we see that the zones with the highest porosity and permeability are in Zone 3 and parts of Zone 2, which means these are critical for oil production. In fact, Zone 3 and Zone 4 are connected, with no dense layer separating them. This suggests that these zones contain around 75% of the oil in place, stored in the reservoir. Now, look at what's happening laterally. If you look toward the southwest SW, you will notice a deterioration in rock quality. This means as you move in that direction, the porosity and permeability decrease, making it harder to recover oil from that part of the field. One more thing to highlight. There is a dense layer between Zone 2 and Zone 3, which acts as a barrier. So, if we want to recover oil from Zone 2, we'll need dedicated lateral sections drilled specifically for that zone. In summary, the Simbox mode helps us visualize how the reservoir properties are distributed, clearly showing where the best zones for production are and where dense layers may present a challenge. Thanks to this model, we have a clear guide on where to drill and how to optimize oil recovery. All right, let's take a look at this showing two images that explain the process of calculating a variogram for different lag distances, which helps us understand how a subsurface property, such as porosity or permeability, changes as the distance between sampling points increases. Left image, 1 lag. In this example, we are looking at data points that are separated by a distance equivalent to 1 lag. The process works as follows. 2 data points that are separated by 1 lag, a specific distance, are selected. The values of the property being analyzed, e.g. porosity, at these points are subtracted from each other. This difference is squared, which removes negative signs and highlights larger variations. This calculation is repeated for all pairs of points that are 1 lag apart. Finally, all these squared differences are averaged, giving us the variogram value for this lag. Right image, 2 lags. The concept is the same here, but now we are comparing points that are separated by 2 lags. As the distance between points increases, 2 points that are 2 lags apart are selected. The values of the property between these points are subtracted, and the difference is squared. This process is repeated for all pairs of points that are 2 lags apart. The squared differences are averaged to get the variogram value for the larger distance. What do these images tell us? The key idea in these diagrams is that as the lag distance increases, the difference between the values of the points also tends to increase. Points that are closer together, 1 lag, tend to have more similar values, while points farther apart, 2 lags, tend to have more differences. By calculating the variogram for different lag distances, we can create a graph that shows how a property varies with distance. This graph is a variogram, which is then fitted with a model to help us predict the spatial continuity of geological properties. This process is essential for building more accurate geological models, aiding in decisions related to resource exploration and production, such as oil or gas extraction. All right, everyone, let's make this variogram exercise interesting and engaging. We've got some data from a well, where porosity values were measured every meter. This exercise guides us through the process of calculating a variogram for different lag distances using porosity values obtained from a well, with measurements taken at 1 meter depth intervals. The porosity values, it was measured between 1 to 7 meter intervals are. Here's the deal. We want to know how these values change as we move further apart, which is where lags come in. So, what's a lag? Think of it as the distance between 2 data points. If you compare porosity values that are 1 meter apart, that's lag 1. If you compare values that are 2 meters apart, it's lag 2, and so on. Easy enough, right? Let's start with lag 1. We compare points that are 1 meter apart, subtract the porosity values, and square the difference to keep everything positive. We repeat this for every pair of points, average all the square differences, and boom! For lag 1, we get a value of 2.214. Now for lag 2. Here, we compare points 2 meters apart. Same process. Subtract, square, average. The value we get is 5.75. Makes sense, right? The farther apart the points, the more different they are. Let's take it to lag 3. We now compare points that are 3 meters apart. The difference is even larger, and when we calculate the variogram, it gives us a value of 7.1. The further apart the points, the bigger the difference is. And finally, lag 4. We compare points 4 meters apart, do the math, and get 7.124. The differences aren't increasing as much anymore. This means that beyond this distance, the values don't vary as much. So, what's the big picture? Look at the curve. At first, the variogram increases quickly, but after a certain point, it starts to level off. This is what we call the sill. Here, the sill is around 7.1, meaning the variation stops increasing much after 4 meters. Why does this matter? Because the variogram is telling us how subsurface properties change over distance. Once the curve flattens out, We know that the data points aren't going to surprise us anymore, even as we move further apart. This is key for predicting what's going on in parts of the reservoir that we haven't sampled yet. And that, my friends, is how you become a variogram expert. Simple, right? Let's keep the energy up and dive into what we can do with this knowledge. Let's dive into variogram modeling and why it's essential for reservoir analysis. But let's keep it interesting. Imagine this scenario. You're working with well data, but you only have a single exploration well. How do you analyze the horizontal variogram? Simple, you can't. There are no pairs available in the horizontal direction. But don't worry, we've got a solution. When you don't have enough well data, you can rely on a secondary source of correlated data, like seismic data. If there's a reasonable correlation, you can use this secondary data to perform horizontal variogram analysis. In essence, seismic data becomes a proxy to help interpret the major and minor range values of the reservoir structure. Here's a pro tip. In carbonate reservoirs with multiple horizontal production wells, the situation flips. You end up with tons of horizontal data and less vertical data due to the well patterns. In these cases, horizontal variogram modeling becomes easier than vertical variogram modeling. It's about leveraging what you've got horizontal data, in this case, to get the most accurate model possible. In summary, whether you're working with vertical or horizontal data, the key is adapting your approach based on what information is available. Variogram modeling helps you understand subsurface patterns, even when your data is limited, making it a crucial tool for reservoir characterization. Now, who's ready to take this modeling approach to the next level? All right, let's jazz this up a bit. Imagine you're a detective solving a mystery, but instead of clues, you have variogram models. These models are not just numbers. They're the keys to unlocking the secrets of the Earth's subsurface. In Petrol, you get to choose from 3 model types to fit your data curve. Think of it as choosing your path in a choose-your-own-adventure book. Spherical. This is your go-to model. It's like the trusty sidekick who's always got your back. It starts off bold and strong at short distances, and then, like a cliffhanger in your favorite show, it levels off sharply. Perfect for robust, stable calculations. This model ensures that the influence of each data point doesn't stray beyond a certain range. Exponential. Here's the drama queen of variogram models. It starts off steep, making big assumptions at short distances, then mellows out, approaching the sill asymptotically. It's all about the long game, making sure every piece of data gently fades out of influence. Gaussian, the smooth operator. If your data shows a lot of continuity at short distances, but likes to switch things up as you move further away, this is your model. It's smooth at the start but gets trickier to manage as distances increase. Perfect for those looking for a challenge in their modeling adventure. And here's a little pro tip. Exponential and Gaussian models can be tricky. They reach their full potential almost teasingly slowly. If you're not careful, they can complicate solving your geostatistical equations. A tiny bit of nugget effect might just be the secret ingredient you need to keep things stable. So, whether you're dealing with porosity or permeability, choose wisely. Your adventure in variogram modeling could define the success of your geological exploration. The image illustrates the concept of search radius in variogram modeling, where 130 meters is a defined search radius. Let's break this down into 2 parts to make it easier to understand. Left side. The colored bar represents a well log with various measured values, such as porosity or permeability, along the vertical axis, depth. The search radius of 130 meters is marked by 2 horizontal red lines, which means that the values within 130 meters up and down from a specific point will be considered during the analysis. The arrows show that within this range, the values are being compared to other data points inside that 130-meter window, both above and below the selected depth. Right side. This plot shows the experimental variogram, where the semi-variance, y-axis, is plotted against the distance, x-axis. The black squares are the calculated semivariance values for pairs of data points at different distances. The red vertical line marks the 130-meter search radius on the graph. It highlights that within this search distance, the semivariance is being measured. Beyond this range, points are not considered in the calculation because they fall outside the 130-meter radius. In short, this image shows how data within a 130-meter window around a well is compared to calculate semivariance, helping to understand how spatial properties like porosity or permeability vary over that distance in the subsurface. The image you're seeing shows how a trend can affect the variogram calculation, specifically highlighting the importance of detrending the data before analyzing variograms. Left side. This is a well log with porosity measurements in percentage on the x-axis and depth on the y-axis. Notice the red line running through the center. This red line represents a trend in the data, showing that porosity is increasing or decreasing systematically with depth. When such a trend exists, the variability of the data points isn't random, but follows a systematic pattern, which can distort the variogram calculation. Right side. The graph on the right is the experimental variogram calculated from the porosity values in the well log. The blue points show the semivariance values at increasing lag distances. The variogram continues to rise without reaching a sill, which suggests that the data has a trend. In cases where a trend is present, the variogram will not stabilize, reach a sill, which can lead to bias in model predictions. Why does this matter? A trend in the data makes the small values appear larger than they are, and larger values appear smaller than they are. This can lead to incorrect interpretations in subsurface modeling. To avoid this, you need to detrend the data by applying a trend function, such as a regression curve. This ensures the variogram properly reflects the spatial variability of the property you're studying, without being distorted by a systematic trend. In short, before analyzing variograms, always check for trends in your data, especially when dealing with porosity, permeability, or other continuous subsurface properties. All right, let's dive into one of the most powerful yet essential tools for reservoir modeling, variogram model fitting. Don't be overwhelmed by all the numbers and graphs. It's the beating heart of predicting subsurface properties, and I'm going to break it down for you in a way that makes sense. What are we doing here? Imagine you're trying to predict how subsurface properties, like porosity or permeability, vary between two distant points. You can't drill every meter to get that information. That's where the variogram comes in, the core of the analysis. At the top left, you'll notice some key values, but two of them stand out, the nugget and the sill. The nugget is like the noise in your data, meaning how much the data varies regardless of distance. The sill, on the other hand, is the point where the curve flattens out, meaning no more significant variation. So, think of the nugget as noise and the sill as the maximum variation limit. What about the models? You'll see we're working with 4 types of variogram models: spherical, Gaussian, exponential, and more. Each model describes how your data varies differently. Think of them as different lenses through which to view your reservoir. The spherical model is the most common and easy to work with. The exponential is for noisier data, and the Gaussian is best for smoother, continuous data. The graph on the right, this is the juicy part. The gray bars represent the experimental variogram, what we're trying to fit. The black dots show how your data correlates at different distances. The blue curve is the model you're adjusting to fit those points. The goal is for the blue curve to get as close as possible to the dots. If you nail it, congrats. You've got a model that accurately describes how your data varies over distances in the subsurface. Why should you care? If you want to optimize well placement in a reservoir or improve resource predictions, you need to understand how properties vary between the data points you have and the ones you don't. The variogram tells you exactly that. It shows how correlated the data is based on distance, meaning you can make smarter, more precise decisions about where to drill. In summary, this isn't just a fancy graph. T is a critical tool for cutting costs, improving accuracy, and making smarter decisions in subsurface exploration. When working with variogram settings in Petrol, you have three main options to make your modeling process easier, more precise, and quicker. Let's dive into them in a way that keeps things engaging. Variogram analysis through object settings. Want to get a snapshot of your variogram behavior in the horizontal direction? You can quickly compute a variogram map and sample variograms for two horizontal directions right from the Object Settings dialog box in Petrol. It's a simple, straightforward way to see how things look before diving deeper. Robust variogram creation using data analysis. If you're ready to get serious and you have your property data in an active 3D grid, this is the method for you. Whether you're analyzing raw well logs, upscale well logs, or the entire 3D property, the data analysis process lets you specify transformations before you even start the variogram calculation. Think of this as a fine-tuning stage for maximum accuracy, direct input for quick variogram simulation. If you're pressed for time or not yet ready to compute an exact variogram, you can simply enter values like range, nugget, and azimuth directly into your facies modeling or petrophysical modeling process. This option is perfect for testing the impact of different variogram settings without having to calculate everything first. Important tip: never rely on the default variogram settings. They're just placeholders. Always check to make sure they match the characteristics of your field before running the processes. And with that, we've reached the end of this module. Party Popper, I'm José Odreman, and it's been a pleasure guiding you through the fascinating world of variograms. Remember what we've covered today, from data analysis to precise settings in Petrol. Now, it's your turn to practice and sharpen those skills. Thank you for your attention. Keep exploring and improving. Be safe, and see you soon in the next module.